is something that we want to solve and that we would like to be able to utilize. So, okay, I can see the presentation. So how do I, do I click on it, or who would click on the presentation?
Yeah, I will do it. I'll do it.
Okay, so, all right. So, okay, so in that case, all right, perfect. Okay, so I give you a bit brief background of what we have at our university, but now let's go back to the presentation, go back to this lecture. So the title of the lecture, as you can see, is Integrated Solar Panel Antenna Design. So we ask ourselves, why would we like to do that? So let's just take a look at the applications, quick applications. I think most of you are very familiar with the concept of solar farm. If we go to some rural area, especially a little bit of a, especially not desertish, but an area with lots of sunlight during the day, then we see rows and rows of solar panels these days. It's not hard to spot them. So with all those big surfaces, as engineer, as any kind of engineer, we first think about ourselves, what else can we do with it? And as antenna engineers, we always ask ourselves, well, can we use that and make it into some sort of self-powered, self-powered stations, self-powered antenna, maybe base station, etc. So can we continue to stay on the previous page, please? Okay, great. So that comes quite naturally, right? We have so many big surfaces to use. And so that's just the one, inspiration for us. And then we also have been talking about smart cars, self-powered cars, electric vehicles. So we ask ourselves, well, can we integrate the collision detection radar antenna with it? And in particular, maybe put all those GPS sensors and stuff all together with a solar panel? That's another question we ask that we would like to do. And of course, it also comes to UAVs or integrating antennas with like a person's uniform and make it into a self-powered radio, etc. So there are many applications, and it just allows us to do multifunctional integration to reduce price and increase functionalities. Okay, next page, please. Thank you. All right. So those are the general applications. There are many applications. Now, meanwhile, when we come to our university, where I'm at, as I said, we are known for our Cube satellite. So the student that is having the thumb up, that's the satellite right in front of him, that little CubeSat, that's the one that we have flown this January. So this is the kind of things that we do here. And a lot of the time, we run into difficulty in terms of deploying the antennas or just buying a separate antenna. So therefore, it prompted this research early on. How can we integrate the antennas with the solar panel so that we can co-use the very limited surface real estate of a small satellite? In particular, the very little cube satellite, because as you can see, for a cube satellite, for any small satellite, what we need, the basic things that we need will be power, solar panel, batteries, telemetry and command circuit, communication circuit, etc. So putting all of that into a very small space is challenging. And meanwhile, to power all of these with just the solar cells, that's put the limit on the power. And therefore, we wrap up solar cells everywhere possible on a small satellite. So basically, it leaves no space for antenna. Even if you want to just put the deployed wire antenna, it will still, pop out from somewhere. So therefore, if we can integrate antennas with solar panels, that will help us tremendously to reduce price and increase feasible science payload. And of course, this can be also used for larger satellites too. So next page, please. Okay, so I've been talking about small satellites and the cube satellites. So let's just give a quick overview on what they are. So cube satellites, they're in a nano or pico satellite family. So satellites are are configured in, filed or put in categories in terms of their weight. So cube satellites are the one of the smallest weights. So they're in the nano or picosatellite family. And other than being small, they are highly modularized, standardized. So you can buy, so everything is standardized. So therefore you can buy panels from one company, frame from another company, and then the deployer from another company, and they can all fit. So with that, you can basically put together a satellite in modular fashion, in off-the-shelf purchasing fashion, like purchasing, you can just do some purchasing from, just like how you do grocery. So that reduces price. Very low cost to develop and deploy. And since I talked about the standardized, and therefore let's talk about CubeSat unit. So the standard is one CubeSat unit is a 10 centimeter cube, and it weighs less than 1.5 kilogram. So that's 1U, and we can put 1U together to do multiple U. So in this picture, you can see 1U, and in the middle, you see 3Us, cascaded 3Us. And of course, if you cut 1U to half, you get 0.5U. So on and so forth. So that's the terminology, and let's move on. And some CubeSat examples. So from top to bottom, from the left, you see two half U, 1U was deploy the panel. So as you can imagine, all the power that is used by a CubeSat is from solar power. So therefore, if you want to do more science, more work, you need more panels. So other than surface mount solar cells, we also have deployed panels. And then the next is 1.5 U. The bottom, we see 3U. Again, 3U was deployed panel. And the most recent Marco antenna by JPL, that's 6U with deployed panel, because you need lots of power. And the Rain Cube, that's again 6U with deployed solar panel. So some examples to give you an idea what we are talking about. We are talking about small satellites without that doesn't carry its own power. The power is only from solar power, sunlight, and therefore we need to cover the entire surface with solar cells. So that puts a restriction. Where do we put the antenna? All right, let's move on. So unique challenges. Again, because they are so small, there are no place for antennas. And most often, the little small CubeSats use deployed antennas, okay, the wires that you see coming out. And the deployed mechanism is such that often we will fold the antenna up and then tie them with a fishing wire, a nylon string. And the nylon string will go out on top of a resistor. When the satellites were pushed to space, you turn everything on, so there's a current goes through the resistor, and then it gets heated up, it cuts the nylon wire, and then the spring pops up. So you can see this entire process is filled with possibilities of misfunctions. If the wire doesn't cut, then it doesn't deploy. Or if it deploys too fast, it might just pop out, just pop out and break off. And as you can see, if the antenna doesn't deploy, then we use the entire CubeSat, right? Entire satellite. That's a lot of money. So therefore, questions to ask and solve is, there's not really a place to put antennas. So where do we put the antennas if we don't want to deploy it? So, or in other words, how do we reduce the deployed mechanism? So let's move on. So one answer, I'm sure you will come up with many other answers. So one answer we came up with here is, let's integrate the antennas with the solar cells. Let's co-use the space. So here are some examples that we have looked into and worked out. So these are the main examples, main techniques that I will share with you today. So if we can do this, if we can put antenna and solar panel together, then hopefully we can reduce the deployed mechanism, and hopefully we can make the most use out of CubeSats. So let's move on. So first thing came to our mind was, all right, so where can we put the antennas if we want to use, if we want to put antenna together with the solar panel? So first thing is, okay, let's put it on top of solar cells. So if we put on top of solar cells, most likely antenna will be flat. So let's say, okay, let's put the patch antenna. All right, the patch antenna will block the solar cells, right? So we said the only power for a CubeSat is from solar power. So we cannot block the solar cells. So how can we make sure we don't block the solar cells, we don't block the sunlight? So the idea comes quite naturally. Let's make the antenna transparent. So to make antenna transparent, we can look into transparent oxides such as indium tin oxide, that's a very popular transparent conductor, or transparent conductors such as silver nanowire, etc. So we can go that route. The only problem is, so far, the antennas designed from transparent conductors have really low efficiency. Their efficiency is somewhere around 30% at the most. And that doesn't quite work for us. So then we ask ourselves, all right, we want the antenna to be transparent, but that's just transparent to light. It doesn't have to be transparent for our eyes. So it's okay if we can see it. So how about we go with the meshed conductor? So that's our first example. Let's move on. Okay, so making the meshed conductor, so obviously we take a patch antenna and we mesh it. Instead of using a flat metal, let's just use a mesh such as a chicken wire, right? So therefore the transparency is defined as the see-through area over the entire area. Okay, let's move on. Let's move to the next page. So some previous studies have been done. The picture, the result that you see on the left-hand side, it tells us if we fix the width of the mesh line, okay, if we have a patch antenna, and if we say the mesh line width is already fixed, then the higher transparency means lower gain, which makes sense. The higher transparency, then you have less line for the current to go through, or less conductor. Of course, that makes sense, right? So all right, so we learned the trade-off between transparencies and antenna efficiency, at least the first thing, one of the first thing. Now, next is we examine, all right, we set the fixed mesh line. If we have to work with this, fine, we will work with this. But what about we fix the transparency? And then where is the width of the line? Let's say we can custom design our mesh. Then the data here that I marked with red, outline, this tells us for a fixed transparency, if we make the line thinner and thinner, we improve the gain. So let's say we have a 80% transparencies. If I make my line really thin, then I can put more lines, so more paths for the current, right? So it does make sense. So that is a great tool, great finding for us. It's very simple, but it's a great finding for us. It tells us, okay, now we can custom design the mesh such that it gives us the best gain and the best transparencies. Okay, let's move on. So with that said, now we are confident that we can put maybe somewhere like a 90 or 95% transparent patch antenna on the solar panel. So now we come down to the next question. How does the solar panel and antenna interact with each other? So to study that, we built several fixtures like the one that you see in this picture. This one is basically a panel of a 1U CubeSat. So we built a solar panel of a 1U CubeSat with all space certified material, and then put the patch antenna on top of the cover glass. As you can see, to make a patch antenna, as you all know, to make a patch antenna, we need a substrate. So the existence of a solar, the cover glass of the solar panel makes it feasible for us. Because of the glass, it acts, the glass protects the solar cells. And because of that glass, we can use that as a substrate for our patch. Okay, so that's our fixture to study. So next we will look into how the solar cells will affect our antenna and how the antenna's transparency will affect the solar cells power generation. So let's move on. Okay, so this picture here, we made a half-U CubeSats panel. I mean, we have many examples, the picture here shows you the solar panel of a half-U, but we have studied many of, experiment in this style. So here it just basically the basic study here is to find out how much power our antenna blocks. Okay, so to do that, we put a non-transparent solid patch and then different transparent patch on the solar cell, and we printed non-transparent patch as well as transparent patch on the glass, and then put the glass on top of the solar cell. So we do that by inkjet printing. You can do screen printing as well, but we do inkjet printing here. Okay, so all right, so with that set up, the results are shown on these two blocks. So from top to bottom, the blue line shows the power generation of a bare cell, the solar cell with no cover glass. And then the next line is power generation of a solar cell with a cover glass. As you see, the power reduced quite a bit. And then the rest is the antennas. So the power generation with the patch antenna printed on the cover glass. So first we see that the biggest blockage of the biggest reduction of the power comes from the cover glass itself. Even though the glass are made extremely transparent, as you make it a bit thicker, it reduces more sunlight. And then the rest, if we could make the antenna transparent, as long as we keep the transparencies somewhere around 80% or 90%, the power reduction is less than maybe 2%. At the most 5% if we cover the entire surface, and we don't really cover the entire surface. The green line is the solid patch. So the meshed patch that we made is, it does still block the power, it still reduce the power generation, but it's a lot better than the green line, that's the solid patch antenna. So here we were able to go back to the system engineer, the power engineer, and say, look, if we make our antenna 90% transparent, in fact, we can make it 95% transparent, then the blocking of the solar power generation is less than 3%. And that is comparable with the shadow cast by those long wires that sticks out, because they also cast shadow, right? Even though they don't block solar panel, when the light comes oblique, it casts shadow. So it's comparable to the shadow that you are already losing. So that allows us to move on with this project, because once the system engineers, power engineer says, okay, I can accept you to put the antenna on the solar cells, then we can move on and to make this project, more mature. So let's go to the next page. All right, so next page is to satisfy ourselves, answer our own question as antenna engineer. How does solar panel or solar cells affect our antenna? So to do that, we put a commercial triple junction space certified solar cells under microscope, and we use that to extract the layer information. So that's the information that I give you there. So as we see, the majority part of our solar cells are semiconductors. Okay, the photovoltaic part are semiconductors, which this is something that we know. The problem is semiconductors, they are not great conductors, and they are not dielectric substrate. So therefore, that means a loss. So therefore, we are putting our antenna on something lossy. So let's find out how much loss our antenna will experience or how much gain reduction our antenna will experience. So let's move to the next page. Unfortunately, that the very bottom part that you are like the dip that you see is where we have to be working with. Okay, so what this tells us is the gain reduction is the highest when the conductivity of that layer, solar cell layer is the solar cell layer below the antenna when the conductivity is somewhere around 1,000 Siemens per meter. That's when we experience the highest loss. And unfortunately, in reality, that's where the conductivity of the solar cells are, okay, from the experimental results. So basically, we will be looking into a lot of loss reduction. Okay, so we say, all right, we will have gain reduction. Can we stay on that page for one more minute, please? Okay, so we say, all right, so we now know we will have lots of gain reduction, antenna efficiency reduction. So I guess this is what we have to deal with. But then we examine the electrodes on solar cells. So in the previous picture, you don't have to go back, but in the previous picture, I showed you the solar cells has a layer, a layer of the that germanium, doped germanium part, that's the semiconductor. And we have electrodes, the lines of metallic lines to conduct DC current. So now we say, okay, how about those electrodes? When we consider the electrodes, let's go back to the next page. When we consider the electrodes, yes, next page. Okay, when we consider electrodes, we noticed the electrodes actually acting as a kind of like isolation layer, blockage between the antenna and the lossy material. It gives us a little bit of the gain back. So we are like, okay, so now we are moving somewhere. We know we are on a very lossy substrate, but due to the electrodes, the loss may not be so lossy or may not be so visible to the antenna. So now let's experiment with it. So these are our experimental setup that we used to, we use this setup to measure the solar cells functionality as well as our antenna functionality. So we put meshed antenna, unmeshed antenna on top of a functional space certified solar panel and did all the measurements on the antenna's gain. So let's move to the next page. Here are the results. So we are looking into somewhere between 2 to 3 dB gain reduction on the antennas due to the solar cells. And this is true for anywhere between 2 to maybe 8 gigahertz. And above that thing, if we stick to the same thickness of the cover glass, then the antenna will, the higher frequency antenna will seem to be further away from the lossy layer, then the gain reduction can be slightly lower. So maybe it will be a bit lower than 2 dB, but 2 to 3 dB is what we have to enter into our power budget or link budget. Okay, now let's move on. All right, so a byproduct here, when we study the meshed patch antennas so that it can be meshed and made it into transparent and put on the solar panel, we also found something that we can play with. My students found out, well, for the meshed antennas, we can assemble them like the first picture on your left. We can assemble them smartly to increase the bandwidth of an antenna. So now we have antenna with a longer bandwidth and it's still transparent. We can put it on solar panel, okay? And that feed line can be always hidden or can be always embedded in between two solar cells, so it doesn't block solar cells. And then moving to the top right, that's where you see again two meshed antennas that we assembled them to give current pass on the two vertical direction, to perpendicular direction, that allows us to make circularly polarized meshed antenna. So circularly polarized transparent antenna that we integrate on solar cells. And The bottom left, that's again a circularly polarized meshed antenna. That's a square. So that's another geometry, right? So it gives us just multiple ways that we can do. And then the red, and then not the red, the round one is an antenna. It's a meshed antenna, and it suppresses higher harmonics. And therefore, when we integrate that with amplifier, power amplifier, it allows us to improve the power added efficiency. So many applications that we can take from the meshing a patch antenna. All right, let's move to next page. Okay, so far we talked about putting the antennas on top of the solar panel. So we have how many options? Let's see. We have a solar panel, so where can we put the antenna? We can put it on top. That way the antenna has to be transparent. Okay, now we can put the antenna at the bottom of the solar panel, right? That's another option. The next, I'll just give you a prediction. We can put it maybe around the solar cells. So, but anyway, before we move to the next one, let's stick to this page. So antennas placed under the solar panel. These are the work that has been already done and flown in space by European Space Agency. So on the top picture, you see those the kind of patch look like gray things or maybe a bit metallic under each solar cells. Those are the patch antennas placed under the solar cells. So as long as the antenna sticks out from the side, okay, let me rephrase it. As long as the solar cells are smaller than the antenna, it doesn't affect the antenna, right? Okay, because patch antenna radiates from the edges. Okay, so you can place it under the solar cells. Now, good thing of this integration is now the antennas will not block solar cell at all. And the solar cells also have relatively minimal effect on the antenna. The trade-off is you see all the gaps between solar cells. Well, you need to leave some gaps so that it doesn't block the antenna. So leaving some gaps makes it less efficient in assembling a solar panel. So that's an immediate trade-off that you could see. So the next picture, the picture at the below, that's another design by European Space Agency. So now they put solar cells closer. And what they did was to make a slot antenna under the solar cells. So now to do that, the solar cells will have to be custom designed, deposited, so it doesn't block the slot area. So it's a custom designed solar cell. As we said before, one of the reasons that a CubeSat can be really cheaply made is we can buy everything from store, not custom design. So this requires custom design, so the price will go up, right? Okay, so the design idea is straightforward. As electrical engineering students, as antenna engineering students, you all know how to design a patch, you all know how to design a slot, and in this application, basically slot and patch are independent. So you could do that on your own. Just keep in mind the trade-off. All right, now let's move on. Okay, so I already predicted this one earlier for you. So the next way to do integration is to put the antennas around the solar cells. Let them not touch, okay? So this is made possible because when we assemble solar panel, the cells are individual cell by cell. There's always some gap in between cells. So that gap, we ask ourselves, how about we put antennas there? So as you know, under the solar panel, oftentimes it's a metallic plate or ground, or just the CubeSat frame. So that's metal. As you know, you can't put the dipole antenna very close to the ground, right? Because image cancels radiation. Therefore, what we can do is we create slot. A slot is a negative image of a dipole antenna. So we create slot and let the slot radiate. So that's the design idea here. Let's move on to the next page, see if we have any experiment. Oh, okay, so we don't have it here. So let's go back. Let me give you the results there. All right, so here, let me just quickly walk you from the left to right. Left is two slot antennas, so two linearly polarized slot antenna placed in between solar cells. The right, we put the cross slot to give us circular polarization. Okay, so So in this design, I mean, we basically, I would say this is a really great design concept. So the challenge, why don't you ask yourself, what is the challenge here? Okay, so the challenge here is the frequency. So the CubeSat, so a 1U CubeSat panel is about this big, right? So you put the slot is limited by the size limit the frequency. So you can only put maybe somewhere, you can only put a slot of maybe a 2 gigahertz S-band antenna on a panel in this fashion. If your panel is bigger, of course, we can create a bigger slot, but otherwise, our antenna will be limited to somewhere like S-band. Okay, so now let's move on. Okay, so now we come to UHF band. So I said so putting the antenna around solar cells is limited to frequencies higher than S-band or somewhere around S-band at least and higher. So how about UHF band? So now you ask, why do you want UHF band? See, this picture here is very similar to the CubeSat that was recently built by our university. So the deployed antennas are UHF band. So we said we don't want deployment, so we need to replace it. So here, basically, we need to replace a UHF antenna. So you ask, why do you need UHF? Why can't we just stick to S-band? So let's visit the link budget. All right, so for an antenna, for a CubeSat, when it's first launched to space, it might be tumbling. You don't know its orientation. Unless we establish a link, unless we can command it to make it rotate, it will be in any orientation, right? When it launches out, it will tumble for a while too. So the uplink, the command link, we need to be able to reach the satellite. Our ground station has to be able to reach the satellite regardless of its orientation. So therefore, in that link, the antenna on the CubeSat has to be omnidirectional so that at any orientation, we can establish a link and talk to it. Omnidirectional means low gain. So now if we look at the phase transmission equation, so the received power on the CubeSat antenna, okay, is calculated from this equation here, phase transmission equation. As you see, one way for us to increase that received power, the received power has to be higher than the noise floor for the CubeSat to process it, right? So if you want to have a certain amount of received power, either the gain of the antenna has to be high, in our case, no way, because it's omnidirectional antenna, or the only thing we can do is reduce the space loss. That's lambda over that 4 pi r square term. Okay, that's a loss due to the distance. So to do that, the only thing we could do is to raise the wavelengths. To raise the wavelength, that means to lower the frequency. So therefore, it limits us to somewhere like UHF and VHF. We don't want to go to VHF because that at VHF frequency, the noise such as galactic noise, microwave noise, in particular, galactic noise is really high. So let's stick to UHF, okay? So sticking to UHF, that means long antenna. Then that means we have to burn wire to deploy it, and it means it may not deploy. Okay, so now let's move to the next page. So that UHF antenna is the one we want to replace. That deployed UHF antenna, that is the one that we want to replace. So to do that, we need a longer slot, a longer antenna. And how do we do that? We can wrap the longer slot around the CubeSat body. So this is one example here. So now we meander the longer slot so that it can further reduce the frequency to the application frequency. So this one, the UHF frequency is somewhere around 490 megahertz. So to achieve that, we meandered it and made it around, and then we proposed, okay, now use a smaller solar cell so that you can place it around the slot. Okay, so we have, so in the last top right picture, you see two meandered line. So one for uplink, one for downlink, and it's placed on a 3U CubeSat. Okay, now let's move to the next page. Okay, so this is some experimental results. So we made a UHF antenna wrapped around the CubeSat body, and then we we have uplink and downlink. The data on the right hand and data on the left top, that's simulate, so that's uplink and downlink, and then we have simulation versus measurement, and then simulated and measured gain. They match up pretty well. This is a circularly polarized UHF antenna, UHF slot antenna wrapped around the CubeSat body. Okay, now let's move on. That's okay. Okay, so we talked about 3 types of antennas now. Antennas placed under the solar cells, on top of solar cell, and around the solar cell. All of these are antennas, like antennas in element level, just one single antenna. We didn't go to the array configuration yet, right? So earlier when I said link budget, I showed you to establish the link from the ground to the satellite, to command the satellite, we need a UHF link. Most often we need a UHF link. Now, the satellite, after it does its science work, it needs to transmit that science data down, such as like a camera or pictures. It needs to transmit it down. So by then, the satellite is already lined up. This is the Earth ground link satellite already lined up, because you have the command to line it. After it lines up, we can have a direct link to go down. So for that link, we need a higher data rate. For higher data rate, we can have a high gain antenna. So here, so the page you don't have to go back anymore. The page in the previous slides shows you many different types of high gain antennas. So we want to go to the array configuration or dish configuration. Okay, let's move on. So this one is an antenna designed by NASA JPL. It's a Ka band reflector array integrated at the bottom side of the solar panel. Okay. So this works really great because the sun is on that side, and then you communicate the data down, right? And the antenna is at the bottom side of the solar panel, so they don't really interact. So for the case where sun and the communication end are on 2 opposite directions, this is a very good solution. Now, how about when the sun and the communication direction is at the same direction? So for example, if a cube satellite want to transmit the data to the TDRS, the relay satellite, and then relay it down, then the sun and the communication and on the same direction. Or the rovers, any kind of rovers, Mars rover or lunar rovers, it will be transmitting to the place when sun and the earth might be on the similar end, right? So in that case, this particular configuration may not work. So let's move on. Okay, so therefore we say to ourselves, how about we design transparent reflector array or transparent array antenna that we can integrate on top of solar panel. So taking the transparent antenna idea, now we go to the array configuration. Okay, let's move on. Okay, so when we move to the array configuration, first thing we come to our mind is array like this. We can just do a patch antenna array. So this is definitely a great idea, but I will caution you on several things. One, we previously have seen that each individual antenna, when we put it on top of the solar cells, it will have somewhere about 2 to 3 dB gain reduction due to solar cell. So we need to keep that in mind. Now we make it into array configuration. We need to see whether or not it will accumulate. Another thing is the feed lines. The arrangement of the feed lines is going to be a bit challenging. Okay, so there are 2 challenges here. But the good thing is everything is on one surface. All right, so let's move on. So in this case, we need to mesh each antenna. So next is, how about we just bypass we just bypass all the meshing. We bypass all the meshing of each individual element and bypass the feed line part. So therefore, we come to reflectory. How about we just have a reflectory and have the feed pop out from a different place, just like an SS Isara, the JPL's Isara. So here, let's talk about some reflectory basics. Okay, so the reflectory, the way we design reflectory is we design the phase response of each element so that it can bend the light to go to make it the radiation to a certain direction. Okay, so normally you can do the bending by concaving the surface, but in reflectory we do that by instead of mechanical changing of the surface, we do that by having each element to have a phase delay. So for a wave that it receives from certain direction, it adds a phase delay so that it goes to bend it to a different direction. Okay, so a slightly different direction. So let's move on. So with that design equations, we design the phase response. Okay, so oftentimes that's how the phase response looks like. So you draw the phase response, that line down, that gives us the size of the element. So that's how we determine at each location what is the size of our reflectory element. And that element can be a patch, can be a patch, it can be some other geometry that I will talk about. Okay, and with that phase response curve, it also allows us to choose a substrate thickness as well as the dielectric constant of the substrate. As you see, the higher dielectric constant of a substrate gives us the curve, more steep curve, so that puts higher threshold on the so that makes each element closer in size. So that gives us a bit of a challenge in the precision in printing each element. So we don't want the substrate have too much high of a dielectric constant. But then that means the substrate will have to be thicker, right? The substrate will have to be thicker. So that creates challenge in putting a thick substrate on the solar panel. And meanwhile, the thickness of the substrates, as you see, if we make the substrate really thin, so if we make the substrate really thin, then again, the curve is very steep, so it makes it hard to print each element, so the substrate has to be a bit thicker. So it's all interrelated. Let's move on. So we have to choose the substrate with the best thickness and the most feasible dielectric constant. So here, as I said, the element can be patch or can be other things. So here so the element can be a loop or a cross dipole or patch. And of course with the meshed patch. So we examined all of those and found out the loop geometry gave us a better performance. Now the loop, as you can see, the light can go through in the middle. Okay, so it's transparent. And meanwhile, it gave us a better phase response performance that allows us to fabricate it. Okay, let's move on. And again, this is more examination on the half wavelength or sub wavelength array. And at the end, we decided we will go with the sub wavelength, a quarter wavelength unit cell geometry with a loop. Okay, so the loop gives us a bit better properties compared to the cross dipole. So let's move on. So this is our final product. So we printed a 8.5 gigahertz an X-band antenna on a 20 by 30 centimeter glass. So is about 6U panel. 6U panel for a 6U satellite. So we inkjet printed the reflectory antenna on it, and then we tested it. So the feed is a 2x2 solid patch antenna, and it can pop out from the other side of the CubeSat. So we can have a CubeSat. We put the reflector on the deployed solar panel and have the feed on the CubeSat body. And of course, the feed can be meshed to make it into meshed antenna as well. Okay, let's move on. Now, here are some results on the gain reduction due to the solar panel for reflector array. We found out the gain reduction is actually a bit better than the element level. It's mainly because this one we are testing at XPET. Okay, so that's the main idea. So again, we are still looking at 2 to 3 dB gain reduction, but the overall realized gain is more than 20 dB. So that made our system engineer quite happy. And the antenna is 95% transparent, so the blockage on the solar panel is less than 5%. Actually, it's less than 3%, because we don't block everywhere uniformly. We don't block it uniformly everywhere. Okay, so now let's move. Okay, so in this presentation, I talked about all the integrated solar panel antenna design. So here I'm just saying a quadrifilar design. Quadrifilar. So quadrifilar antenna, it looks like a helix, quadrifilar helix antenna, but it's not quite helix. So this is kind of just like a homework, or not a homework, just a suggestion for you to think about. So this is not a helical antenna, even though it looks like helix. So I suggest you to take a look at the design properties of such an antenna. It's not quite a helix, right? So that's one thing to study. And another thing is its pattern have this, like peanut shape. That's a really good pattern, because then you can receive signal when the satellite just barely come out from the horizon. It gives a pretty good gain on that link. So it's a nice antenna pattern. Right, so far it's being realized by a quadrifilar antenna, which is not integrated antenna with solar panel. So I thought maybe one of you or one of us can come up with a integrated solar panel antenna design that gives a quadrifilar shape. So that will cover up, so that will solve the problem of horizon to horizon communication for satellites. Okay, so let's move on to the next page. And there are many new designs, such as the one with quadrifilar I talked about, and if you look at the night sky, or if you're lucky, then you will be able to see the Starlink, Starlink by SpaceX, and like all these like a novel antenna design used for Starlinks, as well as the Amazon's antennas. So there are many new designs coming out, many possibilities, and I believe that's where you can play with. And let's move on. Hello, can we move to next page? Thank you. All right, so that pretty much brings me to one of my last pages. So we talked about we talked about different ways to integrate antennas on solar panel. We talked about its application in small satellite or cube satellite industry. So with that, let me give you a bit of a background of myself. I work at Utah State University, and that's in the Valley. Can you stay on the previous page, please, for a minute longer? That's in a very beautiful valley. I hope one day you will visit me here. And I do work with Space Dynamics Lab, and that's our research foundation. So together, each year we co-host a conference called Small Satellite Conference, and this year the conference is really big. We have more than 3,000 people, so it's a really big conference, getting bigger and bigger. So the Space Dynamics Lab, it may not ring a bell to most people, but I want to remind you, in 2020, there was a comet visiting Earth, visiting by us, that we could see it with naked eyes, right? Maybe some of you have seen it. So that comet is called the New WISE comet, and that is discovered by this New WISE, this last telescope that you see at the bottom. So discovered by the WISE telescope designed at Space Dynamics Lab. So that's kind of, my link to all of this. So that brings me to my very last page. So talking about the comet, talking about the stars, I want to close by saying to all the young students and scientists, postdocs here, that you are the real stars. So I believe you will do something great. You will come up with all the great ideas, novel ideas in terms of antenna design or many other design. And I look forward to learning from you. Okay, thank you. That closes my talk.
Yeah, thank you, Dr. Reyhan, for the detailed, nice presentation on solar integrated panel antennas. We have some questions. So before I move on to the questions, maybe I ask Puneet sir, you have some comments?
I think Mahesh, let us take first the questions and then we can have concluding remarks.
Yes, sir. Yes, sir. Yes. Ma'am, we have a few questions.
Sure.
How can we how can we measure the link budget of a solar patch antenna?
Okay, so the link budget, so the link budget is not the measurement, it's more of a calculation. I have another talk that's on just link budget. So link budget itself. So let me just run through it. So the link budget in a nutshell is the received power. So link budget is normally done at the receiver end. So received power by the receiver. So received power by the antenna, it undergoes the loss in the connector, such, some loss in the connector, some mismatch, as well as loss in the filter, etc. Plus the noise introduced by the active components such as amplifier, etc. Okay, so all of that, when it reaches the receiver, it has to be higher than the noise temperature of the receiver. The temperature is affected by the antenna temperature in the system, as well as the receiver. Receivers always get heats up, right? So the heat generated by the receiver. So that's the noise floor. The received power has to be higher than the noise floor. Okay, so that's in a nutshell is the link budget. So the received power has to be so many dBs higher than the noise floor. Now, with that in mind, so the link budget is set with, so how much, so the more received power you have, then if you think of Shannon's capacity, the capacity theorem, then you see the data rate is related to the signal to noise ratio as well as the bandwidth. So received power over the noise floor, that's a signal to noise ratio. Higher signal to noise ratio, higher data rate. But bigger bandwidth, higher data rate. So that's actually the link budget. So you set how much data rate you want and then back calculate how much power you want. And the power from Fritz's transmission equation is reduced by the link loss, but increased by the antenna's gain. So if you want higher signal to noise ratio, you need higher power. Higher power, you get it from high gain antenna. So therefore, high gain antenna, higher data rate. Or at least if you want the minimum power, then at least you have to make your link loss low. That's done by raising the frequency. So that's normally the link budget calculation is normally you can write a MATLAB code, or oftentimes we just use a spreadsheet. You can download some well-known link budgets as well. Yeah, I mean, it's in my other talk, but I can email you some links that you can download a link budget and start playing with it.
Yeah, thank you. Next question is, which type of substrate is better for design of solar patch antennas?
Yes. So to be perfectly honest, we really do not have much choice as an antenna engineer. The reason I say that is we will have to be working with the system engineer. They are the ones, we will have to be working with the system engineers. They are the one to set, okay, okay, the substrate has to be this much transparent. First of all, substrate has to be very transparent, right? And the substrate should not expand or shrink much in space environment in extreme heat and extreme extreme cold environment. And the substrate, the glass, whatever glass or quartz you use, should not darken in the space environment with all the space particle ions hitting on it, right? So it should not darken. So with all that, at the end, the substrate that we can work with basically will have to come from a space industry where they have developed and tested the substrate and say this is space certified that you can use. So we almost have no choice in saying what kind of substrate that we want to work with. Of course, as an antenna engineer, we want to work with substrate with a lower permittivity, so our antenna gain can be higher. But when we are given certain, at the end result, we will be looking at substrate with maybe higher permittivity or substrate with limited thickness, etc. So just for antenna design, we need a substrate with a bit lower permittivity and sufficient thickness so our antenna can have the best gain. But otherwise, we will have to do with whatever is available by sacrificing the gain of the antenna.
Okay, thank you. The next question is, how about 3D printed solar integrated antennas for small satellites?
3D printed. So okay. So 3D printed antenna. So we are not. So you talk about any kind of 3D printed, right? So it can be a dipole. It can be anything, right? Is that the question, or you're talking about printed? So if you want to print antenna just as a flat patch antenna, you don't need a 3D printer. You can just have an inkjet printer. But when you want to print 3D, such as a dipole, etc., so that's feasible. But again, big question is whether or not this 3D printed material is strong enough to handle extreme heat and extreme cold. That's one. Two, very importantly, any material that you have in vacuum condition, it will blow out bubbles. It will breathe out it's called gas. It will put out gas. So the material that you have should have a very low outgassing. Otherwise, on the ride from the Earth to space station, or just during the ride from the Earth to space, if it gives out bubbles, it will contaminate other much more expensive satellites. So it's feasible, but you have to be careful with the material selection. The material has to be strong, and it shouldn't change its properties in cold and hot, because if it changes property, it affects our antennas, and it should not blow out bubbles. So low outgassing.
Okay, thank you. The next question is, the transparent reflector array, whatever you have shown, is it also made of the conductive mesh?
So you can, but the result I show at the end is made of a conductive loop. It's a loop traces, because we found out for the reflector array geometry, the loop traces functions better than the mesh traces, and loop is a lot easier to print and it's more transparent. So it's loop. You can do loop, you can do cross, but we found out loop is better.
Okay. The last question is, any limitation on mesh size or shape?
Yes. So the patch antenna is limited by its frequency. So therefore higher frequency, you will have a smaller patch. And then meshing the smaller patch in higher frequency is gonna be harder, right? So the meshed patch antenna, the best application of meshed patch antenna is somewhere between L band to X band. After X band, meshed patch antenna is gonna be challenging. So you might have to think of something else, or just mesh it, maybe just several lines so that it's not highly transparent, but because the size is already small enough, so it's still okay to put it under cover glass.
Okay, I think that's all the questions we have. Thank you very much.
Let me make a comment. For the higher frequency, such as X band, higher than X band, the Ke band, we go to higher frequency for high gain antenna, right? Lower frequency, we use it for combined link. Higher frequency is the downlink high gain antenna. So for high gain antenna, oftentimes we are looking into array geometry. So that's where we went. I went to the reflector array geometry, and for reflector array, we found out the loop geometry is better than the mesh. So that's just follow up on the question. Okay.
Yeah, thank you, Dr. Reyhan, for answering all the questions. Now I request Puneet sir to give his concluding remarks.
Yeah, thank you, Mahesh. Thank you very much. And I take this opportunity to once again thank Dr. Reyhan for providing a very wonderful, insightful, and a very in-depth presentation on solar array cum antenna or integrated solar panel and antenna presentation. I think, especially because I belong to the space industry, I see a lot of value additions and futuristic things going to happen in this particular field. And with this presentation, I can surely say that the researchers, especially in the space domain, will definitely look this aspect and try to start activities in India as well, because in this particular field we are not very we are in very nascent stage, but this presentation will give them an idea how to start and how to circumvent the problems which already people like you have faced, so that we are not doing we are not re-engineering the same wheel, but we are starting from the lessons learned from you and building new products. uh, so hopefully we would like to see you, Dr. Reyhan, again in MapCon. If you can come and join us in Bangalore, it will be really wonderful for us, and we can meet physically. And then our students and young professionals and researchers, they will have more time to interact with you and learn from you. Thank you very much.
Thank you. And I hope one day you will all visit Utah State University for the Small Satellite Conference. That's where you will see all the, basically everyone from space industry comes to that conference. So I hope to see you here someday.
Sure. We would like to participate.
Yeah. Thank you, Dr. Rehan, for your time and the effort in delivering the lecture. And we are also thankful to your university for showcasing all the results whatever you have got. And say our thanks to Professor Cynthia first. We had last year we had lecture from her to our chapter students, and it was a really nice talk, and most of them were students who attended this talk. They'll really benefit from this talk, and thank you once again for giving us the lecture. And I like to thank Puneet sir for joining, and also all the participants who have joined this distinguished lecture by Dr. Rehan. And thank you very much. Thank you, ma'am. Thank you very much. We'll close the session.
Have a great day. Thank you. Bye.
Thank you. Bye.